Okay, I'm going to start recording here. So please let me know if you can hear me or not. So before we get started talking about physics, thank you, David. Before we get started talking about physics, so just a reminder, we do have our second test on Friday at 9:30. The Zoom sessions are getting set up right now, so eventually they should all be set up before Friday morning. So, and the format is essentially the same as our first test. And I also wanted to mention that I'm running an extra office hour this afternoon. So I'm going to run office hours from 1:30 to 3:30. So there's an extra hour there. So if you have questions about things that are going to be on the test, you should come to the office hours. And if you can't come to office hours, you can go to a TA office hour, or you can post questions on PHYS. And we'll all do our best to answer your questions about things. So are there any questions about any of that? I don't know when the final exam will be yet. I was sent a tentative schedule, but it hasn't been finalized. No, you don't need to submit another photo with your ID. No, the one that you submitted already, it's fine. Is the final in GoSFU? Okay, sounds like they might have finalized it then. Good. What did they, last time I checked it was April 19th, but I don't know if that's changed. So anyway, so if there are no more questions, then we're going to go ahead and get started. So we're finishing up chapter 7, and then we're going to do a little bit of chapter 8. No, I don't usually record my office hours, so thank you for the time of the final there. Great. Okay, so here we go. Let's find my slides here. Here we go. Okay, so up until now, we have been looking at basically, we've been treating all objects like point-like objects. I mean, we've been looking at boxes and balls and various other objects moving around and cars and animals, but we've been treating them all like point-like objects. And now we're going to move ahead and start looking at extended objects. So objects that have a size, and we're going to start looking at things like what happens when those objects rotate or roll or things like that. So we're kind of going beyond point-like objects now and into extended objects. So one of the first things you need to consider here is basically, how do you apply the laws of physics to an extended object? It can be quite complicated, but there's one simplifying situation that you can apply, and that is that if you can figure out where the center of mass of an object is, the center of mass of an object will behave like a point particle with that net external force acting on it. So, for example, if you have a ball rolling down an inclined plane, can be quite complicated, but the actual center of mass of the ball will act like a block sliding down a plane with that force, that component of gravity, mg sine theta, pointing down the incline. And similarly, if you take a stick and you throw it through the air, it can rotate around, but if you track the position of the center of mass, you'll see it does exactly what we expect a particle to do when it's thrown into the air. It acts like a projectile, and you get your parabolic path, as shown here, where the net external force in this case would be just our force due to gravity pointing towards the center of the Earth, right? So here's a nice actual scenario that shows you a real object. In this case, it's somebody doing a motorcycle jump, and not only are they doing a motorcycle jump, they're actually flipping as they go across here. And if you sort of pinpoint roughly where the center of mass of the person, the motorcycle rider, and the motorcycle is, you can see that it roughly follows that parabolic path you would expect for a point-like particle. So So that's why center of mass is important for us, and that's why we're going to figure out how to find the center of mass for different kinds of objects. So how do you figure out the center of mass for an object? So essentially what it is it's the average location of the mass, okay, of an object, if you have an extended object, or a collection of objects. So here we have a collection of objects. We have three masses, M1, M2, and M3, and we have them labeled and on a graph, and we also show their position vectors, R1, R2, and R3. And if you want to figure out what's the position vector of the center of mass, RCM, then what you do is you take each of those position vectors for each individual mass and you multiply by the mass. Okay, so you have M1 R1 plus M2 R2 plus M3 R3, and then you divide by the total mass. In math, we would call this a weighted average, because you're weighting each position by the mass. So the bigger the mass, the more that position vector is weighted, the closer the center of mass will be to the location of that mass. Okay, now most of the time we won't do this as vectors. We'll do this as components of the position vectors, or in other words, we'll do each of our different dimensions separately. So we can figure out what's the x position of the center of mass by adding up all of the x positions times the masses and dividing by the total mass. And you can do the same thing for the y, and you can do the same thing for the z if we go into 3 dimensions. So that's how you would figure out where the center of mass of a collection of masses is. If you wanted to find the center of mass of an extended object, we're going to try this in a minute. There's a couple different ways to do it. In general, you would want to do integrals like this, but we won't do the actual integrals in this class. We'll just look at the results of the integrals. Because remember, when you go from discrete separate masses to a continuous object, then those sums become integrals. That's essentially what an integral is, right? It's a sum over tiny, tiny little bits. So RCM stands for the position of the center of mass. That's the position vector that points to where the center of mass of the collection of masses is. Okay, so what I thought we would do is give this a try. Now, you don't necessarily have to do the math here. I'm going to do the math for you afterwards to show you how the math would work. But what I would like you to do is, just by looking at the sizes of the masses and the locations of the masses, see if you can guesstimate where the center of mass of this collection of masses is. And I'm going to give you some choices here in a poll. Okay, so there's our poll. All right, and so what I want you to do is just try and guesstimate. So you've got an XY coordinate system here, and we have a 4 kilogram mass that's at position 4 on the x-axis. We've got a 5 kilogram mass that's at position -3 on the x-axis, and we've got a 7 kilogram mass that's at position 2 on the y-axis, +2 on the y-axis. So thinking about, so that means we've got a total of 9 kilograms on the x-axis and 7 kilograms at a position of 2 above the x-axis. And then we've got 4 kilograms to the right of the y-axis and 5 kilograms to the left, but the 5 kilograms a little bit closer. Okay, remember, this is mass times position. And so the first number there would be the x position of the center of mass, and the second number would be the y position of the center of mass. Okay, I think we'll do about 10 more seconds. So just guess, because this is a guess right now anyway. So if you're not sure. Okay, 5, 4, 3, 2, 1. So let's have a look at the answers. Okay, so as you can see, sometimes it's kind of hard to guesstimate, but the majority are going for the two answers that are actually quite similar to each other. So it's probably hard without doing the math to actually figure out which of those two is the right one, but it looks like a lot of people think it's either C or D. So why don't we go ahead? So what I'm going to do now is actually do the math to show you what this looks like. So I'm going to switch over to my camera. See if I can get this to work. Okay. So hopefully you can all see that. Okay. All right. So how would you figure this out? So let's start with the X center of mass. So the X position of the center of mass. Okay. So what did we have? We had a 4. So remember, we're doing the sum of mi xi divided by the total mass, just to write that down again, right? That's how you would calculate center of mass. All right, so let's see. Okay, so we're going to start with, we had a 4 kilogram mass, and that was located at a position of 4. And then we have a 7 kilogram mass, and that was right on the y-axis, right? So that means it was at a position of 0. And then we had a 5 kilogram mass, and that was at a position of -3. And then we need to divide the whole thing by the total mass. And the total mass is 5 plus 4, which is 9, plus 7, which is 16. So we divide the whole thing by 16 kilograms, and what you get for the X center of mass is about 0.0625. Okay, which is approximately 0.063 if you go down to 2 sig figs. Okay, so that's the X position of the center of mass. And now we're going to do a similar thing for the Y. Okay, I won't rewrite the formula, but for the Y, the formula looks the same, except you have YI instead of XI. Okay, and so what do we get? So for the Y, remember, 2 of the masses were on the x-axis. I mean, they have y is equal to 0. The 4 kilogram mass, I'm going to write it out so you can see it. 4 kilogram mass had a y position of 0. And the 5 kilogram mass also had a y position of 0. But then the 7 kilogram mass was at a position of 2. Okay, and again, you're going to divide the whole thing by 16. You always divide by the total mass. Doesn't matter where they're located. All right, and when you do that, what do you get? You get that this one is 0.875, which if you go down to 2 sig figs is 0.88. Okay, so that's what we get. So now let's go back to sharing the slides again and see what the answer was. And so here's the math again, so you can see it again, right? And so we can see, like I said, the first one's 0.063 and the second one is 0.88. And so answer D. And so, and most of you thought it was either C or D, and it is a little hard to tell which of those Y's would have been right. So that's good. So you can see that you can guesstimate this answer, right? So when you're doing these problems, once you've done the math and gotten an answer, you can then look at your scenario, or even before you start, you can look at your scenario and say, about where should it be? And then see if your answer agrees with your intuition about where it should be. Because usually with center of mass, you can get a rough idea of about where it should be. Okay, so that's center of mass. So that's for point-like particles. We treated these masses like point-like particles. So what if you have an extended object? So like I was saying before, with an extended object, usually you're going to do an integral, but if you have an object with a nice symmetry, sometimes you can find the center of mass by breaking it up into pieces whose centers of mass you already know, and then treating those center of masses for those extended objects like point particles and combining them. So I wanted to show you what this might look like. So say you have a flat board, say, that looks like this. We're going to do this two-dimensionally. Okay, so you have a rectangle that looks like this, and you have another rectangle, same size rectangle, so same width, same length, okay, placed like that. So you have an L, and we're going to try and figure out where is the center of mass of this L combination of two flat rectangles. So this one they both have length L and they both have width W. Okay, they're the same rectangle. So if the density is even, then the center of mass of each of those rectangles will be at its geometric center. Okay, so this is where their center of masses for each of the two separate rectangles would be, basically halfway up and halfway over. Okay, so what we're going to do now is combine those two to get the overall center of mass for the combined object. So you want to put in an XY coordinate system so that you can figure out where you are. And then you'll have an origin, and then you can measure your X's from that and your Y's from that origin. All right, this one we're going to do with a slide. So our X center of mass then, all right, would be, so what you can see here is, so M is the mass of each of the rectangles. And so it's M, for the bottom one, it's M times L over 2, because the center of mass is halfway along the length. And then for the vertical rectangle here, the one going up the y-axis, right, the X position is just W over 2, the width over 2, okay, because it's just halfway across the width. Okay, and so you take those, divide by the total mass, which is 2M, right, the sum of the two masses, and you get L plus W over 4. So you can see the mass cancels out, right, and we just get a length, which is what we want. So you need to have only units of length, right, for your position of the center of mass. For Y, now, what do we do? So starting again with the lower mass, the lower rectangle, you can see that it's the height of its center of mass is just width over 2. The trickier one is what's the height of the center of mass of the rectangle along the y-axis there, and that is going to be the whole width of the bottom rectangle plus half the length of the top. So it's width plus L over 2. Okay, and then when you simplify that one, you get MW over 2 MW. That's 3W over 2 times N. So you pick up a 3 here. And again, the masses cancel out, and you end up with 3W, 3 times the width, plus L over 4. Now, it's a little hard to figure out exactly where that is, but so what I'm going to do now, just to make our lives a little bit easier, for these rectangles, the length is roughly 4 times the width. So let's set L equal to 4 times the width and see what we get. So if I plug in 4 times the width for L, I get that X center of mass is 5/4 the width. And if I plug L equals 4W in to the Y center of mass formula, I get that the position of the Y position of the center of mass here is 7/4 times the width. And so where is that? That's about there, roughly. Okay, so that's where the center of mass of these two rectangles would be two-dimensionally. Okay, and it's kind of, so if you look at it and you think about it, it's closer, you know, it's to the left of the center of the bottom rectangle, closer to the vertical rectangle, and that seems to make sense. There's a lot of mass to the left there. Okay, and then it's not halfway up the vertical rectangle. It's between the middle of the vertical rectangle and the bottom one, closer to the bottom one, because there's a lot of mass along the x-axis there. So if intuitively that seems to make sense. One thing to notice too is that the center of mass of this extended L-shaped object is outside the object, and that will happen sometimes. For example, the center of mass of a donut that has a hole in the middle is in the hole, is in the middle of the hole. Okay, that's where the mass is centered. All right, so there's not always going to be mass where your center of mass is located. All right, so I don't know if there are any questions on that. Well, why did you use 4W? I just wanted to give us a number that was easier to make it easier to figure out exactly where the X and the Y were located. So for these particular rectangles, the length is about 4 times the width. So that's why I wanted to do that. Okay, so now I think we're going to do another poll question. And this one's on some extended objects here. So we've only got 3 choices. Okay, so we have a uniform disk in 1, and it clearly has its center of mass at its center. And I marked where the center of mass was. Okay, and it sits on that yellow dotted line. And so the question is, suppose the disk is cut in half and the pieces are arranged as shown in 2. Okay, so you basically cut it in half and you took the top piece and you flipped it upside down. Okay, the question is, where is the center of mass of 2, of configuration 2, compared to 1? Is it higher? Okay, so closer to the top of the page. Is it lower, closer to the bottom of the page? Or is it at the same location? And think about what I just did with the 2 rectangles, how you might figure this out. Okay, I think maybe we'll do 10 more seconds here. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. All right, let's see what everybody thought. Okay, so what do we see? We see a bit of disagreement, okay? Our largest group, 71 people, say that the center of mass of 2 is at the same place as the center of mass of 1. But a reasonable size group think, no, in fact, it's A, it's higher. And there's also a reasonable size group, the smallest group, are going for lower. So let's see how we would figure this one out. So basically, the way you figure it out is this, okay? If you think about those two semicircles there, the center of mass of each half of those, each part there, is closer to the top of the semicircle than the bottom, right? And then the center of mass of the whole system will be located at the midpoint of the two semicircle center of mass. So it'll look something like this. Okay, so each of those semicircle center masses is higher than the center, right? Okay, it's closer to the flat top where there's more mass. Okay, and then the actual center of mass of the combination is halfway between those two. And that point, because both of those black dots are higher than basically the half height, the center of mass will be higher than the half height of the whole configuration. And so the answer is that yes, in fact, it will be higher. All right. So the center of mass changed when we took that top piece and cut it off and flipped it upside down. We put more mass higher up, and that shifted the center of mass up. Okay. Any questions on how that works? If you flip it the other way, then it would go the other direction, right? So if you flip it the other way, then both the center of masses would be below the half height of each piece, and the whole thing would go lower. If the bottom piece was also flipped, I think it would probably stay in the same place, right? Because then they would be equidistant from that center. Good question. So, okay. So also, I forgot to mention that we have Laura here to answer our questions. So I'm going to keep going, and if you have more questions, she can try and answer them. So one thing I wanted to mention, and something that we'll come back to later, is that we often talk about the center of mass of the human body. And this is kind of a funny cartoon I found online once, where it's just talking about how your body shape determines where your center of mass is going to be. So like small children tend to have a relatively high center of mass because their heads are big compared to the rest of their bodies. Whereas depending on whether you've got more weight in your hips or more weight in your chest, that'll make a difference as to how high your center of mass is. Women typically have somewhat lower centers of mass for their height than men do because of different mass configurations in their bodies. And the other thing that has an impact on your center of mass is whether you're carrying something. Or whether you're not standing straight up. So this is labeled CG for center of gravity, but essentially center of mass and center of gravity are at the same location. Okay, it's where the force due to gravity acts. So you can see, for example, if you have a child on your shoulders, that shifts your center of gravity up. If you're carrying a heavy bag on one side, that can shift your center of gravity to the side. Okay, and you typically, as we're going to see when we talk about stability, want to make sure you keep your center of gravity over your feet. Because if your center of gravity is not over your feet, if it goes back or forward relative to your feet, then that's when you're going to fall over. Okay, and we'll come back to this when we do more on stability. So now we're going to move on. Yes, so center of gravity, center of mass are essentially the same thing. So we're going to now talk about rotation, which is, so now we're moving into chapter 8. So here is, say, a record or a turntable of some kind, and we're looking at a position x there at time t1. And we know if this object rotates counterclockwise, then at some later time t2, that position, that, say it's a piece of gum or a bug or something, we're going to do our ladybug simulation again in a minute, has moved, right, to as the whole object rotates. Okay, so that x is fixed on the whole circular object and the whole thing rotated around. Okay, and it basically rotated by an angle delta theta. And so delta theta is what we call the angular displacement. So when an object has rotated by some angle, okay, we say it has undergone an angular displacement, and we will be measuring angular displacement in radians, okay? And we'll probably shorthand that to rads, okay? Remember that the way you go between degrees and rads is that 180 degrees is equal to pi radians, all right? So it's really important, as you'll see in a minute, that we do everything in radians here, because otherwise the units won't necessarily work out. Okay, so the next quantity we're going to look at is how fast is an object rotating, and we call that the angular velocity. So just like we did with linear motion, we're going to define an average angular velocity to be the displacement divided by the time elapsed. So we're going to use omega, Greek letter omega, which is like a curly W. Okay, so the average angular velocity, omega average, is just the angular displacement, delta theta, divided by the time elapsed, delta t. And the units, pretty much almost all of the time, we will be using radians per second. Sometimes, in some problems, they will give you units of revolutions per second or revolutions per minute, RPMs. And remember, a revolution is 360 degrees or 2 pi radians. Okay, and so it's easy to convert from revolutions to radians by just multiplying by 2 pi. Okay, so that's how fast an object is moving. And then we're going to have another convention here, which is that when you're looking straight on at the object, okay, positive angular velocities correspond to a counterclockwise rotation, and negative angular velocities correspond to a clockwise rotation. So that's the convention that we're going to use. Okay, so this is when you're looking at an object and the axis about which the object is rotating is pointing at you, is coming out of the page. The pre-lecturers like to talk about it being like a z-axis, okay, that's coming out of the page at you. All right, so I thought we would play around with our ladybug revolution just for a little while. So you might remember this one from before. So let's see if I can get this one to work. Okay, so this one's a little small, so it might be a little hard to see here. But so here's our ladybug, okay, on our turntable. And what we're going to do now, so I've got this set up so it's measuring angular velocity in radians and angular displacement, radians per second, and angular displacement in radians. So say we make this, I'm going to make it +2 for my angular velocity, and then we're going to start it going. So this is a constant angular velocity here. Okay, and so we've got a graph of angle versus time is the top graph. The second graph is angular velocity versus time, and the bottom graph is velocity. So this will be the linear velocity of the ladybug. And so we let it go. Okay, and so positive angular velocity, so it's going counterclockwise. Okay, and this graph probably looks, these graphs, I'll stop it there, probably remind you of our position versus time and velocity versus time graphs that we had when we were doing linear motion, so we can see the angle increasing, right, with a constant slope there. So that's a constant angular velocity. You're going to have a constant slope for the angle versus time. You have a horizontal line, slope equals 0 for angular velocity versus time. That's a constant angular velocity. And then the actual linear velocity of our ladybug, so this is the magnitude of the velocity. So the speed is also a constant. And it's kind of hard to see there, but you can see the little vector here. We've got our centripetal acceleration, and we've got, because this ladybug undergoes centripetal acceleration, as we know. So we can also, I think I can put the beetle on here too. All right, I'm going to actually clear this and try and start it again. Let me get the beetle up there. Stop. Actually, I guess we can keep going. See if we can see that. I don't know how well you can see that. You know, I'm going to reset that and try again. Oh, you know what? He's not moving, is he? He's not quite on the turntable. All right, let me reset and start again. All right. So I want that one. I'm going to put him on here too. Okay, so now we have the beetle. And clear my graphs. Okay, so now let's try, say, -2. So now we have a negative angular velocity. Okay, so now what will happen? Let's have a look and see what happens. And so you can see we're going to stop. Doesn't want to stop. There we go. Again, you can see now the negative slope for position versus time and the negative constant angular velocity, because now we're moving clockwise. And it's a little hard to see, but there are, the speeds are here. You can't actually see, I don't know if I can make it so you can see. You can't really see the beetle's speed here, but the beetle, you can see from the size of the vectors that the beetle has a higher speed because he's further out. You can see the number here. The beetle has a speed of 7.1 meters per second, whereas the ladybug has a speed of 4 meters per second. This is the magnitude of the velocities, but their angular velocities are both the same. Okay, and actually, yeah, I guess the angles are slightly different here, the ladybug and the beetle, because they're at different places on the turntable, and so they're measuring from a different starting point. Okay, so that's what this motion looks like. All right, so let's go back now to all right. So we saw the clockwise, the counterclockwise motion, and we saw the constant angular velocity there for our ladybug and our beetle. All right, so let's now think about, say we look at a point on the outer edge of a circular turntable like that. So yes, so let's see what this looks like. Say we are at a radius r. Okay, so say the circle has a radius r. Okay, we can calculate, you might remember this from math class, we can calculate the arc length. So we can calculate how far that red X has moved during this time span. Okay, and the arc length, you might remember, S, is equal to the radius of the circle times the angular size there. So in this case, our angular displacement, delta theta. But this expression, the S equals R delta theta, only works if your delta theta is in radians. And that's why I think we should always only use radians for these problems. So if a problem gives you other angle units, like revolutions or degrees, first thing you want to do is convert things to radians, okay? Because this part of it where you're going from angular quantities to linear quantities only works if the angles are in radians. Okay, so the arc length is r times delta theta, and then we can use that to figure out the size, the magnitude of the linear velocity of a on the outside of the turntable because we just take the arc length, which is the linear displacement, divided by the time elapsed. So that's our r delta theta divided by delta t. But then we say, wait a minute, but delta theta over delta t is just our average angular velocity. Okay, so this is just, so our speed, the magnitude of our linear velocity, v, is just r times our angular velocity. Okay, and technically, I guess just to be a little bit careful here, if you want the magnitude of the speed, then that should be the magnitude of the average angular velocity, because it could be negative there. Okay, because we know this is the magnitude of this vector, right? So this is essentially the velocity that an object moving in uniform circular motion would have, right? It's that velocity that's tangential to the circular path. Okay, so it's the size of that vector we're talking about here. Sometimes people refer to it as the tangential velocity. And just to show you how the units would work for this, okay, so if we have meters, say for our radius, and we have radians per second for our angular velocity, but we know that velocity units or speed units are meters per second. So one thing you're going to notice is radians are kind of a weird unit because they're a dimensionless unit. And so they don't have dimension of meter or second or mass or anything. And so radians can come and go. So this is a case where a radian will disappear. All right, so when you go to solve for what's the speed of this little red X on this yellow circle, okay, you're going to plug in your angular velocity, say in radians per second, and your r in meters, and then you're going to cross out that radian and drop it, okay, so that your final speed will just be in meters per second. That's one of the weird things that happens in rotational motion, and we'll see that over and over again as we do rotational motion problems. So another topic they talked about in the pre-lecture video was rotational kinetic energy. So I'm not going to get into a lot of detail of this one. The main thing to know about rotational kinetic energy is that it's 1/2 I times angular velocity omega squared, where I is what's known as the moment of inertia of an object. And we're going to get into detail in a minute about how you figure out moment of inertia. But it's, in a way, it's kind of like center of mass, except instead of doing m times x, you're doing mass times r squared, where r is the distance from the axis about which you're rotating. Okay, so if you have a collection of masses mi located at a distance ri from the axis, and you want to figure out the total moment of inertia of an object, which essentially just tells you how hard it is to rotate the object. Objects with big moments of inertia are hard to rotate. They will take more force to get them going, or more torque, as we're going to see, right? But objects with smaller moments of inertia, okay, with more mass close to the axis, give you a smaller moment of inertia, will be easier to rotate. And you'll kind of get a hang of this. And then once you know what the moment of inertia is, so you can see, right, in our kinetic energy formula, 1/2 I omega square, that looks a lot like our linear or translational kinetic energy formula, 1/2 mv squared, where the I in that expression acts like the mass, okay? It basically tells you how hard it is to get that thing going, and it tells you once you've got it moving at a certain speed, right, the more inertia, right, moving at a certain angular velocity, the more kinetic energy you're going to have. Okay, so that's how that's going to work. I thought we would do a moment of inertia calculation. So here's kind of a typical object. So this is an L-shaped object. So we've got 3 small masses connected by extremely light rods. So that means we're basically going to ignore the mass of the rods. So it says, assume that the masses shown are accurate to 3 significant figures. So even though they only gave us 1, we'll assume that those have a couple zeros afterwards. What is the moment of inertia of this object about the x-axis and about the y-axis? All right, so we're going to try and do this one. So I'm going to switch to my camera now. Okay, here we go. Hopefully you can see that. I wish I could show both things at the same time. I have to see if there's a way to do that so we could, because it would be useful, right? So let me just really quickly sketch it so you can see what it looked like again, right? So we had 1 kilogram here, we have 1 kilogram here, and we have 2 kilograms here. So it looks something like that. This is our x-axis, this is our y-axis. This is 3.3 meters here, so now we have a length to it. And now this is 1.8 meters. Okay, so let's see if we can figure out how to do this. Okay, so we're gonna figure out, so part A was about the x-axis, right? Okay, so again, let's write down the formula in general. So it's the sum of mi ri squared. Okay, and now the x-axis is our axis for the first part, so we need to measure how far away things are from the x-axis. All right, so what does that look like? So if we want to figure out how far away things are from the x-axis, that's just the y's of the objects, right? So we could rewrite this for the first part as this is just going to be mi yi squared. I'm going to add up over the 3 objects. All right. So I is 1 kilogram, right? So let's do this one first. This one's at 1.8 meters. Oops, I lost my point. Right, and then we've got another 1 kilogram at 1.8 meters. And then we've got 2 kilograms, but that's sitting right on the axis. Okay, this is the axis for part A. Okay, so that one doesn't contribute at all. Okay, so we don't even have to write it down, right? We can just say +0 for that one. Okay, so if an object's right on the axis, it's going to not contribute to the moment of inertia. And this is going to give you 6.48 kilogram meter squared. Okay, so that's what we get about the x-axis. Now let's try about the y-axis. So similarly, this time about the y-axis, we just need the x positions of everything. So this is going to be some mi xi squared. Okay, and so this was about the x-axis. I could call this ix, this one, and now let's call this one iy because it's going to be different. So this is interesting to see, is it depends on the axis. Okay, so again, this guy's right on the y-axis, so this guy's not going to contribute. So we're going to have 0 for that one, and then this one is 3.3 meters away, so it's 1 kilogram times 3.3 meters squared, and then this one is 3.3 meters away too, so it's 2 kilograms times 3.3 meters squared, like that. And so we get a much bigger number. We get 32.7 kilogram meter squared for that one. So a much, much bigger number. All right, so we're running out of time. So yes, I will put these calculations up after class. So what I want you to think about is look at these 2 numbers. Think about why, when we rotate about the y-axis, when the axis looks like this, why is it so much bigger than when we rotate about the x-axis? And we'll talk about that next time, about what that means and how it matters which axis you rotate around. And essentially, it matters how far away all those masses are from that axis. Okay, so I'm going to stop recording now.